Hello. Hopefully you all can hear me. I'm Carter Emart. I'm from the OpenSpace team at the American Museum of Natural History. OpenSpace is a NASA-supported, NASA Science Mission Directorate supported. Are you there, Adam? Okay. Okay, I'll hang up with you. Sorry for the comedy of errors getting started. What you're viewing is OpenSpace. It's an interactive data visualization engine. It's really, and we call it an engine like a gaming engine. So it's utilizing high-end graphics. You can download it freely. It's open source from OpenSpaceProject.com. We're an academic collaboration between the American Museum of Natural History in New York, Sweden's Linköping University, the University of Utah, and New York University. And so this is goes to the sort of foundational work that was started as a Millennium Project for the Hayden Planetarium replacement, upgrade, the new Hayden Planetarium within the Rose Center for Earth and Space at the American Museum of Natural History. The stars that you see in the background, I'm going to confine myself to planetary science today. I'm just showing you briefly what it can do. But suffice to say that when the planetarium was sort of rethought as a Millennium Project, we thought, well, how can we go from stars on the ceiling to data visualization immersion to tell the stories of the cosmos? So with that, the ideas around what OpenSpace is here as an interactive tool began. For the Hayden Planetarium, we create productions. I direct those productions, and those are really meant as productions that are based in data visualization as far as we can go with that. So what you're viewing here right now is both our interface and a number of things. The lines, I'll turn off the trails of the planets through the solar system. I'm leaving one trail of the ISS around Earth. The Earth that we see here, I'll also just turn off some of the filigree details that are in the upper left. I'll turn off the graphics of the display, which I'm purposely leaving on to sort of show you some details. But this is the Earth yesterday. Why yesterday? If I just bring this up and go to now, we will see that, I'll just clear the clock here, is that I actually should be seeing some data and maybe paging in. But currently, the daily mosaic that's being created, in this case by the SUMI NPP satellite, if I want to see those layers that are available and open this up, we have, we could actually add a number of different layers from NASA's Global Imagery Browse service, but let's just check in with, say, the Aqua imagery. Okay, so that's the Aqua satellite, and that it's near polar orbit, and its sections as it maps the Earth did not exactly have coverage that filled the gaps over the equator. Aqua and Terra go back to about the year 2000, and all of those daily mosaics are atlased. If I was to switch to the SMPP, we have this set, I think, for actually, if I hit the now button, I'm actually going back a day, or actually going forward to now, and seeing the resulting of mapping that's incomplete. So we have to gather the data. Imagery has to be gathered by the satellite, the downlink, and then the preparation for it to be online at NASA Goddard. And so that's for Earth. We add in a Rayleigh scattering atmosphere. Let me just come closer to illustrate our partnership. Actually, if I turn this off, we'll see what's being revealed underneath the Rayleigh scattering. atmosphere here is the Earth in higher resolution thanks to Esri's world global high resolution service that we have, and so that we can come down, fly over Mount Orogenes and so on. Grand Canyon, if I was to come in just to look at that, here we see White Sands, New Mexico. And I'll just try to fly a little bit toward the Grand Canyon, tip over so to highlight a Rayleigh scattering atmosphere, Rayleigh and me scattering. And it's been generalized so that we can apply it to other planets. And I'm flying really fast, and the internet speed has been a little challenging today, so bear with me. And so I'm just going to come down, similar to other Earth browsers, most notably Google Earth, but also, this technique is now used in many different companies in different ways, but here OpenSpace avails us to, of course, see the Earth and with Rayleigh scattering. Also, the stars should fade out. I forgot to turn that on, so we're actually seeing the stars through the atmosphere, which of course would not be the case. But what we do is to apply globe browsers generally across the worlds of the solar system where we have data. So let's turn our attention quickly to that of the moon. I'll come out. And once again, crossfade, I had, again, I was trying to show if there was any mapping that was available earlier today. I saw it just peeking through the eastern limb here, basically the westernmost coverage of the satellite so far. So actually, if I just go back a day, there we go. So we're seeing that global coverage. This satellite data is quite nice. It goes down to 0.5 kilometer in resolution. Okay, so let me just clear the decks for that. And if I want to turn on the satellites, this is not all the satellites, but a selective number of them, that certain ones in low Earth orbit, and then on out to geosynchronous. So we can see their relative rates, differential rates. Of course, coming from a museum and academic teaching institutions, this is really we see OpenSpace as an educational tool, but with its foundation in data visualization is in the importance of actually showing real data. These satellites are illustrated from the latest and downloaded when we load OpenSpace. Satellite tracks 2-line elements from CelesTrack, and so let's see. Oh, late admitting our partner here for the booth, the Illuminati. We have worked with them over the years. They're a display and multi-solution company for everywhere from sort of portable planetariums to big installs, and they also work with the Jet Propulsion Laboratory and with the Eyes on the Solar System, which also plots missions. We do mission visualization as well within OpenSpace, but primarily this started as an endeavor to visualize for planetariums. Our institutional partners within the funding for OpenSpace, the massive funding, are the Adler Planetarium in Chicago, the Marson Planetarium at the California Academy of Sciences in San Francisco, Gates Planetarium in Denver, Baker Planetarium in Houston, and also in North Carolina, Museum of Nature and Science, or Natural Sciences in North Carolina, which is not a planetarium. So suffice to say, as I move out now, that OpenSpace is really meant to draw maximum context through visualizing really the entire universe. So OpenSpace operates on a selected target mode. So what I'm going to do now is just target the moon. And what I've set up for us here, I'll turn off the satellites, I'm going to come in on the moon where I've actually turned the shading off. Right now it's kind of new moon, so the near side would be pretty much, Mars is going to be my next target. So we're seeing the sun in view, so we would not obviously be illuminated on this side right now. Let me come in to the Apollo 17 landing site. Coming into Taurus Lytra, what we're looking at right here is the wide-angle camera mosaic. I'll mention that some of you may know of NASA's TREX system that allows for education as well as professionals to look at multi-layered data and context. We actually share some of the work that we're doing with TREX, and we can also take TREC data and put that in to OpenSpace. We're coming in on that wide-angle camera mosaic, which is 100-meter resolution, and then we're coming in now to an inset that was created by lead author Haas, but as a collaboration between the USGS and the German DLR. And so we're coming in over this LROC blended mosaic of the an augmented Apollo 17 Taurus Lytra Valley landing site. So I'll bring you down to EVA 3, and this is Station 6, and of course the boulder split rock that had rolled down North Massif, giving them a geologic sample from higher in the stratigraphic column. And what we've done here is I just come in slowly. It's loading all this as we go, and some of the data actually coming in live off the internet should have been obvious from when I was showing the Earth data. As I come in, we're coming up on photogrammetry. I showed this at LPSC 2 years ago, also working with the Illuminati immersive booth. But these are the boulders that were done in photogrammetry by using the EVA photography by Jack Schmidt and Gene Cernan on our last lunar EVA in December of 1972. So, of course, we can come up very close to see this imagery. We used reality capture, commercial photogrammetry software to string this together. Where obviously the low resolution patches are where we're seeing there is no model, so we're sort of seeing holes in that. If I bring myself out just a little bit and navigate around, I can bring us around actually to Jack's footprints. I know they're Jack's footprints because if you view the video, you can see that Jack was swirling around between the boulders over here, and so we can see his tread marks in 3D in the soil. Let me just stop my drift here as we come in and whoa, yeah. Give me a second. I want to change my approach. Big white screen. I always hate that. But I'm trying to turn my camera around so that we can look at the vesicles on fragment 4 and 5 over here. And of course, there are samples. And another partner in the Science Mission Directorate Science Activation Collective that we are part of are the Lunar Materials group from the Lunar Receiving Lab there in Houston. And so they have some of the samples that were taken off this particular rock. So let me just bring us out into up close and personal, which the Hasselblad photography allows us to get really detailed on some of the geology, even of these samples. And the images are, in fact, in color. So let me just turn around briefly, and I'm going to move out and away and retarget myself for the lunar module. And so I'll just focus on that for the moment. And Challenger was the lunar module on Apollo 17. We can come over and we'll see a full resolution LROC inset, about a 1/4 meter resolution here that we've placed a photogrammetry model of the LEM from the Smithsonian, dressed out to look like Apollo 11, in fact. But clearly at this scale now, we're seeing a delineation between both the sort of foot treads of the astronauts, dark in the light dust, or the light or the dark dust having been blown away by the descent engine, and then dark being re-exposed sort of by the treads of the astronauts' footprints, but also the parallel tracks of the rover. You can see the rover parked in the background there to the east, so that it could view the lunar module on ascent when it lifted off, of course, the ALSEP stations, and so on. So this shows how OpenSpace does several things. One is that we can put models that are of objects very small within a overall scene, which I alluded to in the beginning, goes all the way out to 3D model of the universe based on astronomical catalogs. I'm focusing here today, of course, on planetary objects because of this conference, but I could fly out into the stars. So let me now turn our focus to Mars, and once again, this sort of navigational paradigm that I choose a place that I want to go to and fly out to, and then cycle around. So here's Mars, just coming up close in open space. I know the height map is on because I can see the Tharsis Montes dark sticking up through our atmosphere. Also, I'll stop time because I could see that was evolving. And so this is the Mars Global Surveyor wide-angle camera mosaic that we carefully actually took shadows out by dividing with a hillshade from MOLA. Why? Because we wanted to actually use this template for color to colorize other data sets. So if I just do this, I will now see this is the Viking color mosaic, where we're actually blending in our color atop the coloration that typically comes with, which has more of a blue component. So we had worked carefully on this coloration for our space show development, and then we apply it here in OpenSpace. If I come in closer to Valles Marineris, we come in over some of the high-rise material. This I've had some issues with internet speed today, and the number of layers that I'm trying to show. And so let me just come in. This is the Viking mosaic, and it's sort of struggling to come in. We have the atmospheric model tuned to that of Mars, conditions of Mars. And now I'll just attempt to show, in this case, open up Mars. If you can see this screen, let's open up Mars. I have basically imagery layers, the color layers, and the height layers. So with this, I have basically the color from the Mars orbiting cameras of the MGS global mosaic, colorizing the Viking. Well, let's actually come down here and turn on Murray Labs, Jay Dixon's blended CTX map. I'm going to turn off the Viking, and so they're not potentially using the internet to download both. And also atop that, served by Esri, we have the high-rise set that have terrain models attached. So we'll be reading that elevation as well. This I'd like, this is what I've been struggling with today, to actually be snapping in really fast in demonstration mode. But I am, driving this all in real time. So I'm using my mouse to just drive us around to explore this. So let me come in, Western Kandor-Chasma, Seti Mensa, the layers here that we can see. And at this point, what I'd like to do is, not to confuse myself, I'm just going to come down now. I'll open up the height layers. I have basically MOLA and high resolution stereo camera global elevation that we are using. I can augment that actually with terrain of CTX based on the AIM stereo pipeline that covers this particular area. And maybe what I'll do is I'll turn off the global just so that we're seeing the elevation of this model from CTX derived. Maybe, wait a minute. Okay, we'll use the one from 2018. Now you can actually see where we had data and where we did not. And so our MOLA at our resolution of MOLA is about 400 meters at the equator. Using high resolution stereo camera, Trend here at USGS has processed that in the map that's available down to 200 meters. But we get about 10 times that resolution if we're using stereo CTX coverage. So let's just come into that, and I'm sort of waiting on the downloading of the of Murray Labs blended CTX map. Also the high rise, and that has been coming in slowly. I'm coming over a particular patch, just kind of waiting for that to happen. I'm sorry for some of the experiments that we're running through on this first day, having some issues with that. Boy, it's frustrating me. But anyway, what OpenSpace is doing is loading a lot of this together. And so we do cache, and so I was struggling to get the cache working just before this time came up. And so suffice to say, maybe this is struggling a little too much. I'll try to turn off the high-rise layer, and let me just see if I can then look across the terrain from CTX. That was done by high school students of mine from a top achieving high school in the New York tri-state area called Bergen County Academies. One of those students has gone on for a PhD at the University of Hawaii, and that's Kiara Ferrari Wong, who's attending LPSC, and I'm not sure if she's watching this particular presentation. If you are, Kiara, I'm trying to turn on your 2019 version of the layer, and I'm struggling. So let's just say, suffice to say, I'll pull up and out of this. Let me try to go over to Jezero to if I'm saying the word Jezero properly. Perhaps I'm butchering it because I'm not a Spanish speaker. My apologies. But let's head over in that direction. You'll notice the low contrast here of the Dixon map. This is kind of inherent from the blending that had to be done for the different conditions represented in all the CTX imagery. There's also a sort of horizontal banding we see here. This was a beta 1 version that Jay Dixon was kind enough to let us use. You can also see holes where there was a lack of data when this was processed. So let's go. I'm going to rotate Mars backwards here so that we can get over to Syrtis, northeast Syrtis, and Jezero crater. So let me just bring this back and rotate back a little bit more. And in this case, I actually have one of Dixon's. I'm going to turn off this global map that was struggling. We go back to the map that we see from our. Let's see. I could turn on Viking. I'll leave on Viking with our global color. But we'll come down now into our area around Jezero, and now I will attempt to turn back on the I don't know, the high rise. High rise is on. Huh. Let me see. Under maybe I'll turn Viking off. Looks like I'm in lower. Yeah, and I don't understand. I actually think the high rise that I've been struggling with today may actually have an issue with the server side, and that's another thing to check since I'm flying live. But here we should see Jezero Delta with the CTX product from Murray Lab, and I've turned on global map. I have the MOLA HRSC. I'm going to turn off the high rise just because I think that's problematic. Could be the computer we're accessing. And I do have the CTX Terrain turned on for Jezero, so that let me clear all this out, so that we are seeing as a characterization at CTX resolution of Jezero as well as the surrounding terrains, and also our atmosphere, so that we're seeing the high rise has selected areas that would take up probably about 30% of screen right now, but the CTX does allow us to have a broader view at resolution of terrain that's on the order of about 20 meters. The Northeast Syrtis region, of course, which was a possible landing site candidate. Maybe if I drift all the way over to the obvious lava flows that were coming in the region, we can see those and explore those again three-dimensionally interactively. I'm not sure if there are any questions, and Adam, I'm not sure if you're monitoring that.
I do not see any questions at this point. I do now have the ability for them to live chat us in the YouTube chats, so they can chat us while they're watching.
And I might ask you to pass those to me because it's kind of confusing for me to have the streaming software, the actual software, and the YouTube on at once.
If we have a question.
So thank you.
Yep, I'll ping you if there's a question.
Great. How much time do we have left?
I would say probably wrap up in about 20 minutes.
Oh, wrap up in 20 minutes. Okay,
yep.
So this is a longer time window, I guess.
Which is a 1 hour window.
Okay. And so we're obviously getting our sea legs today. So yeah. It's interesting that I actually think based on just what I'm seeing is that our high-rise service may actually have an issue at Esri today. So that's always a possibility, and that's why I wanted to fly with the cache. Anyway, that's as I say, we're sort of just getting our stuff together today. So why don't I pull back away from Mars a bit and show a couple other things. Let me see what I might have available. I had set this particular file up so that that I was focusing on Moon and Mars. But what I mentioned how OpenSpace really is a browser that can show even more than the solar system. So let me pull out. Maybe I'll show a couple things in the solar system. If I do, make sure I have the sun in line and move back far enough. I'll probably see a big label come up for Mars in a second, Mars and Earth, just to show us where we are. And let's see if I have ability to show the asteroids here. So we'll open up the solar system. Okay. I think also, I did not load those. I did not load our asteroid categories, which we have. Again, to streamline this essentially for a presentation that was really about Perseverance on its way to, fortunately, safely. We did this presentation a day before with a collaboration with the Lunar Planetary Institute, USRA, and 3 astronauts the day prior to the landing of Perseverance, which we're very happy came out on target and all safe. As I pull away from the sun, we're beginning to now actually sort of brighten the sun, because we're going to see it in context to that of the local stellar neighborhood. To the right, in the lower right, we see Alpha Centauri. I'm not sure, I don't think capturing my cursor, which I could use as a pointer, but I'll put it right behind the sun, nearest star to us, of course. And now I'm sort of, I've rotated the screen so that the Milky Way becomes our new sort of horizontal view. And as I pull away from the sun and the solar system, I'm now seeing to 4¼ light years out to Alpha Centauri. And if I continue moving about, we see there's some other stars that have kind of come off the wallpaper of the nearby stellar neighborhood. That's passing above the sun right now is the star Sirius, and above that Procyon. Sirius is 8 to 10 light years away. We see Orion still very much together as a constellation. Those stars are over, well, the nearest one is about 300 light years away. And so right now, Alpha Centauri passing, we're only about 5–10 light years out. Now we can see some stars in the background having parallax with the sun and Alpha Centauri. Alpha Centauri is about the same brightness as the sun, the brightest of the triple star system that it is. And so it's closer to us right now, so it's a little bit brighter than our sun. But behind that, we can, if you know the night sky, you might recognize the 2 bright stars that are kind of moving with my parallax. So if I use the sun as kind of my pointer, and the sun's in the middle, there's the star Vega, about 20 light years away. Even closer, 16 light years away, is the star Altair. These make up the summer triangle in the night sky, along with the star Deneb. Deneb is about 2,000 light years away, so we don't expect to really see much motion there. If we were concerned with exoplanets, which of course this conference is, allow me to bring this up, and I'll close my solar system category. I'll open up my Milky Way. I'll go into our exoplanets. We have the dynamic exoplanet, and also has the ones that have been confirmed also with Kepler. But there's the Kepler footprint. So now the context, I mean, I can turn on labels for these, but again, that can start to crowd the screen. Let me just do that for a second to open these up and come down and draw my labels. Oh, they're too large, so I'm going to bring my text size down, and so that we see which ones are closest, because they're going to be sorted sort of by screen size. And now I'll pull back a little farther. Proxima Centauri with its candidate, well, this planets that we know of, and so on. So in this way, we can march on out. Another interesting thing that we try to show is the following. Let me close up the exoplanets and just come in for constellations. And if I show constellations here, we'll see their connection, star-to-star connection. This only sort of makes sense. So there's Cassiopeia behind the sun, the W. If I come back over in this direction, we'll see we see Orion and the exoplanets. Actually, let me turn off the dynamic discoveries. I'll keep the yellow dots, which are from Kepler. After its reaction wheels had problems, and we had these other groupings along the ecliptic plane. So right there is Taurus, that's behind the sun. If I move over, we now see Gemini, and then Cancer, and Leo, and Virgo, and so on. So we can see those from Kepler. And once again, if I just come back to, that's along the ecliptic, there's the main footprint. So, okay, we made these constellations, one, because it's an obvious starting point so far as understanding the sky. But quickly, as we move out into space, of course, constellations are just asterisms that we recognize in our night sky. Some are fairly dim stars that are close and thus recognizable. Some are really bright stars at a distance. And so as you come out, it quickly sort of becomes a pincushion. And when we do this as well, okay, I see the Milky Way in the background. I'll level out the Milky Way. And at this point, you start to say, well, how far away are we? One of the things we add in here as well, if OpenSpace, if it's anything, it's all about transformation matrices between sort of our equatorial coordinate system for Earth, the ecliptic system for that of the solar system, and then the galactic coordinates that make sense for the data sets that make up everything beyond the solar system. An atlas that was assembled at the American Museum of Natural History 20 years ago so that we could make our spaceship productions. And one of the things that we found most useful as we began to go out were to depict these grid systems, but in a way that here I'll bring on one that was actually illustrated in the book Cosmos. So Carl Sagan actually talked about this. What I'll do is I'll dim this down. It might scintillate a little bit. But this, in combination with the constellations, star-to-star connections, illustrates, of course, we're in the center. We're illustrating a sphere around us that's some 85 light years in radius. This represents radio. As the Earth became radio bright in the 1930s, with ever more powerful radio, and then also the development of radar just around the time of World War II. These signals moving out, and so the speed of light represents a sphere, some 130, 140 light years in diameter, 85 light years in radius, and so this becomes a kind of prominent marker for us if we want to consider where we are in the greater Milky Way. Well, we see the band of the Milky Way. Also, the stars, I could brighten all the stars for us, but I'm sort of keeping them now in a sense of visual magnitude we might see with our human eyes if we were out there. Oh, in fact, in coursing in front of us, however seen backward, is our model that we actually built for our first production of the Orion Nebula. So we're now, I know from just a distance here, we're 1,500 light years away, about 500 parsecs in distance from the Earth. And so if I move out far enough, and we can see the exoplanets creating a view cone on out, well, now it changed to a visualization of the Milky Way galaxy from a dynamic model that's from Japan, that took into account position, velocity, observations of gas clouds around surrounding us. And so we see both a stellar distribution as well as a volumetric visualization of a model that was spun up by about 100 million light years, about half an orbit. It takes us 250 million years to make one orbit around the galaxy. And if I pull back far enough, we augment that additionally with the outlier from a particular galaxy that, as far as we can tell, is very similar to the Milky Way, that of NGC 1232. We can see the Magellanic Clouds at a distance. I'll just come up here. I'll turn off the stellar component of the stars in our Milky Way model. So let me do that. And so that makes the galaxy a little more visible as we pull out into the local group of galaxies. Maybe I should turn on the labels for that. We're moving out into a three-dimensional data set of about 30,000 galaxies assembled by Brent Tully at the University of Hawaii. So his data set reaches out. Then we switch over to the Sloan. What's nice about Tully is that basically we see everything that sort of surrounds us in all the main galaxy clusters. So I'm just looking through this. I'm going to close my Milky Way, I'm going to close up my grids, open up the universe data set, and just within galaxies, you'll see these are the different clusters that we have. And so if I open up Tully, how are we doing for time, Adam?
I would say probably wrap up in about 5 minutes or so.
Oh, that's perfect. Okay. So my Tully labels. Oh, actually, let's see. I'll turn on the voids. Okay. Voids, labeling, and my Tully galaxy. I had the wrong group selected. Tully galaxies. Come down here, draw my labels. Great. So now clear the screen. So now we are seeing basically, I wanted to show Andromeda here and sort of highlight our local group. Of course, Andromeda is about 2.5 million light years away. M33 is sort of a smaller, more humble companion perhaps to Andromeda. Andromeda, Milky Way, they're roughly about the same size. There was sort of assumption that Andromeda was larger than the Milky Way, and then maybe reassessments, or perhaps the Milky Way is larger than Andromeda. Regardless, it is blue shifted, and in about 5 billion years, and the sun's running out of its last fuel before it goes red giant, it's a time when we expect to collide with it. So let's go out farther. And actually, if I go up in this direction, we should see, crossing over local void, and a little bit to the right over here, is the Virgo cluster, 65 million light years away, about 1,000 galaxies. And so in this way, mapping our local surrounds. And just triggered by moving out far enough, we should see now the Sloan survey. The coloration is that of sort of nearest neighbors, the sort of density, if you will. And also we can see the effects of sort of the fingers of God that are pointing back at us. Of course, we're using velocity to get distance, and then there's the peculiar velocities of the individual galaxies around their own cluster center of mass, and that tends to then spread out the distance equation. This is being actually looked at by Tom Jarrett and others at the University of Cape Town in South Africa. We're about to have a presentation at the museum looking at this, where what they're doing is attempting to qualify membership to different galaxy clusters and collapse those back in to take out take account of the peculiar velocities. Another thing we see out here is a lack of data around essentially the Milky Way plane that blocks our view for efficiently sort of picking up galaxies that are now sort of out to about 1 billion light years away, as we are. But here, clearly, especially on the left, which corresponds to the northern view from Apache Point Observatory, and looking for the Sloan survey. To the right is the southern observations, or the southern sky, which as you can see from there. Just looking at Sloan, we have other galaxy groups we could bring in. But we can clearly see on the left the large-scale structure, and on the right as well, that the cluster of voids and superclusters of galaxies and so on. Farther out are the quasars. We see less structure there, but we're really looking at very bright objects that are at great distance. Perhaps what expect is that when gas was still present in galaxy formation, and also galaxies building themselves up from various collisions, that there was more gas available and falling in on supermassive black holes that seem to be in the center of all galaxies, and so that make them visible. Beyond that, imaged in 2015, the latest view of the cosmic microwave background by the Planck satellite. And here, if we step on out, we're sort of outside of time. So it makes no sense of nice sort of seasonal Easter colors here. But the slight temperature variations, of course, are what are being visualized here. Of course, exaggerated so that we can even see them from almost total smoothness. But that the blue area is cooler, where galaxy clusters will form, and the warmer areas of expansion that will become the voids that we see writ into our more local and more present in time view of the universe that's closer to home. So all the way from vesicles on a rock on the moon on out to as far as we can see, OpenSpace contextualizes all of this by being able to sort of move across scale, which is important, of course, in any kind of astronomy teaching scenario. This is the vast scales that are involved in this cosmic process, the generic process, of course, that makes stars and planets that we're all studying here, and of course the very important question of life is there any other life out there? Is life special to Earth? Seems to almost be absurd looking at the scale of this. Every point that we were seeing of every little galaxy represents, of course, hundreds of billions of stars, perhaps trillions of worlds. I'll just come on back to Earth. I was set for Mars. Once again, if you're interested in OpenSpace, OpenSpaceProject.com. It's open source, freely available, works on Windows and Mac, and you can compile it on Linux. I'll select Earth, and we'll come on home. And I want to thank Illuminati, who we work with, because they create innovative displays worldwide, and work with other partners like the Jet Propulsion Laboratory, Eyes on the Solar System, visualizing missions. We also do that to some degree as well, and do that for planetariums. Eyes on the Solar System does, and Eyes in general, because it does more than just mission visualization, but does that tremendously for your own personal devices. We tend to focus on machines that can accommodate a large graphics card. Here we actually see today's current coverage. Messed around with time and flew all the way out. But this is as much of the Earth as we see currently with the Sumi MPP satellite. Thanks, Adam. I've probably gone beyond my time.
No worries. Excellent. Thank by clicking on join the live stream link on the Lunar and Planetary Science Conference booth, or by visiting the Illuminati YouTube page. So thanks again so much, Carter, and looking forward to another couple sessions tomorrow.
Excellent. Thank you.
All right. Take care. Bye-bye.